Okay, so let's try system of differential equations. So the rate of change of x depends on x plus 2y, and rate of change of y depends on 4x plus 3y. Where x and y are functions of t, and their initial values are x of 0 is 1 and y of 0 is 3. So let's try to think about what to make of this. The first thing you can do is you can rewrite this as a matrix representation. So you can rewrite this as xy prime equals to the matrix of coefficients, which is 1, 2, 4, 3. So 1, 2, 4, 3. And then times xy. Now, some of you forgot how to multiply matrices, so let me quickly review multiplying matrices. How do you multiply? Across and down, right? That's how you multiply matrices. So you multiply 1, 2, and xy gives you what? 1 times x plus 2 times y. That's what you get if you multiply the top row. And then the second row times this gives you 4 times x plus 3 times y. So that's the matrix you get if you did the matrix multiplication. By the way, if you multiply a 2 by 2 matrix with a 2 by 1 matrix, this is 2 rows and 1 column, right? Then the resulting matrix is a 2. So these two dimensions has to match. And if you multiply these two matrices, the end result is a 2 by 1 matrix, which is 2 rows and 1 column. Okay? And then if you compute this and see what it means for this to equal to that, it really means that x prime should be the first row, which is exactly this thing here, right? And then the y prime is equal to this second row, which is 4x plus 3y, which represents this one. Okay. So that's the first trick. Okay, so in other words, whenever you're given a system of differential equations, by the way, this is first order. If you have a system of first order differential equations, you can rewrite it in terms of a matrix form. There are ways to solve this differential equation without using the matrices, but that's harder. So I will just go straight to this method using the matrices. Okay. Now the next thing that you want to do is to find out something called eigenvalues of this matrix. So let's leave this for a while. And I'm going to talk about eigenvalues of a matrix. What's an eigenvalue? Eigenvalue and eigenvectors. Okay. It's the following concept. I want to find out a matrix A, B. And by the way, this one is called a column vector. A matrix of form n by 1, n rows with a single column, is called a column vector. There's also something called a row vector. There will be a matrix with dimension 1 times n. That means you have one row and many columns. Those are called, these go by the name of column vectors and row vectors. And by an eigenvalue and an eigenvector means it's a vector whose product with this matrix is same as just some constant multiple times A. That's what an eigenvector is. Graphically, what this means is that if you have a 2 by 2 matrix, 1, 2, 4, 3, you can apply this to any point on the plane. So let's say you have any point, say 1, 0. Then it gives you what? 1, 2 times 1, 0, 1 times 1 plus 2 times 0, that's 1. 4 times 1, 0, 4 times 1, 3 times 0, you add them, you get 4. So what this does is it's a function that takes a point to a point. So you have a point 1, 0, and under this function, if you multiply this to this, it gets sent to 4, 1, which is somewhere here, 4, 1. And you can really think of this as a function that takes a vector, a column vector, and it sends to another column vector. So it takes this column, this vector 1, 0, and takes it to another vector. So you can view a 2x2 matrix as a function from a vector to a vector. And what we are looking for is we're looking for vectors which don't change the direction. Possibly it could be pointing to the opposite direction, but it's still along the same line, and it's just resizes. Okay, those are called eigenvectors. Okay. Now, sometimes A and B ends up being complex numbers. Sometimes A and B happens to be two real numbers. We can actually prove mathematically that a 2x2 matrix will have at least one eigenvalue with an eigenvector. But but you can't know if you have two. It's good to have two, but sometimes you may only end up having one eigenvalue. We will only deal with the case today for the case when we have two eigenvalues. And also these column vectors are real. Okay, now I'll try to link this with this and explain why this will give you a solution to that later. But let's first focus in trying to find out what this means. Okay, what are these A and B's and lambda and A and B? Okay. Well, first think about it like this. This is if you do across down to multiply, this is 1 times A plus 2B, and this times this gives you 4 times A plus 3B, and I'm trying to set this equal to lambda times A and B. So this, if you multiply this is lambda A and lambda B, and we're trying to set them equal to each other. So you end up with the following: you have A plus 2B equal to lambda A, and you get 4A plus 3B equal to lambda B. Moving this to the other side, you get A minus lambda A, and moving this to the other side, you get 3 minus lambda B, right? So you can still transform this as 1 minus lambda A plus 2B equal to 0, and 4A plus 3 minus lambda B equal to 0. Okay. Right. We already know that there's a solution to this. What is it?
0.
0, 0 is the solution, right? So there's a trivial solution to this equation. But we are not interested in the trivial solution. So when we say eigenvectors, this is not allowed to be the 0, 0 vector. It can't be the 0, 0 vector. At least one of the A or B has to be non-zero. That's the first condition. We want non-trivial. And then if you look at this and say, if 0, 0 is already a solution, we're trying to find other solutions other than 0, 0. But if you have a system of equations with two unknowns, so think of lambda as some given value. So think of this as a equation of two unknowns with two equations, right? Then you're supposed to get either one solution, or it could be how many solutions can this have? If two equations, two unknowns. No, you can have A as a number and B as a number. So one pair, you get one pair of solutions for that. But then we're trying, because we already know that 0, 0 is not a solution. We're trying to find more than this. Okay. And the only other way to get other than this pair is when you have infinitely many solutions. Does that make sense? Because usually, like, if you have 2x plus 3y equals to 1 and 5x minus 2y equals to 2, if you have an equation like this, you get usually one solution. Why? This is a line in the plane, right? That's another line in the plane. They're going to intersect once, right? Now, is it true that all lines intersect only once? All pair of lines intersect only once? Is that true? What else can happen? You can have parallel lines. In that case, no solution. And what else? The two lines could be the same thing. In that case, you may have infinitely many solutions. Okay? Now, to say that you want solutions other than 0, 0 means what? Which case? You want how many solutions? Infinitely many solutions. You want this to be infinitely many solutions. Okay? So, in order to find an eigenvector that's not 0, 0, satisfying this requirement, it forces us to say that this equation must have an infinitely many solutions. Okay, now let me go back and explain what that means in terms of a matrix. Okay, so I kind of went from the matrix notation to regular equations to get that, but this can be written again in that form, right? If you write that form, what's the coefficient matrix? What goes in here? I want to say A, B. What goes in here? 1 minus lambda. 2. 4. 3 minus lambda. A, B, and this is? No, look at the right side.
0, 0.
0, 0. Okay. So from now on, we're not going to do all that work and do the following. Whenever we start out with the matrix notation for the differential equation, we're going to skip this and just go straight from here to here. Now, what is this again? This is lambda, the what we call the eigenvalue, subtracted from the diagonal. So when you have a square matrix, this side is called the diagonal. When you say diagonal of a matrix, it's always this direction. This is called the anti-diagonal, right? Diagonal means only this one, backslash, okay? So this is the diagonal. You subtract lambda off, and this will be the equation that you write down for the eigenvectors, okay? Now, if you view the equation for eigenvectors in this way, then something suddenly pops up. Do you remember how to solve an equation of this type for matrices? If this is a matrix, and that's also a matrix, and you want to find x, what do? You multiply A inverse both sides, right? And these will cancel, and giving you x equals to A inverse of B. That's how you solve a matrix equation. So if you apply that same theory here, you would be multiplying the inverse of this, and you multiply the inverse of this matrix times 0, 0. What would you get? If you multiply any matrix times 0, 0, you're going to get 0, 0, right? Okay. So if the inverse of this matrix did exist, then the only solution you get is A equal to 0 and B equal to 0. Right? Now, is it true that all matrices have inverses? No. When does a matrix not have an inverse? When the determinant is 0. Okay? So the only way for a non-trivial solution of this type to exist is if the determinant is 0. Okay? So let me actually erase everything and wrap up the discussion so far, because I want to show you the method for finding eigenvalues. Okay? Eigenvalues and eigenvectors. So this is what you're going to do. You're presented with this system of differential equation. You will immediately write it in the matrix form, and then you're going to write down the matrix obtained by subtracting lambda off the diagonal, and write down this equation for the eigenvectors. Okay, eigenvectors and eigenvalues. A comma B is called the eigenvector, and lambda is called the eigenvalue. And you're going to say that the condition for such equation to have a non-trivial solution AB is that when the determinant is equal to 0. All right, now let's find the determinant. Okay, AD minus BC. So what does that become? That's 1 minus lambda times 3 minus lambda minus 8 equal to 0. This is lambda squared minus 4 lambda plus 3 minus 8 equal to 0, which gives you lambda minus 5 lambda plus 1 as its solution. You can see that the 3 minus 8 is negative 5, and the two numbers that multiply to negative 5 and add to negative 4 are negative 5 and 1. And if you solve this, you get lambda equal to 5, and you get lambda equal to negative 1. Okay. So we found out the two eigenvalues. These are the eigenvalues. And then once you find the eigenvalues, you can plug them back in here to find the eigenvectors. Okay. So you have two cases. Case 1, that's when you have lambda equals to 5. And if you plug in lambda 5, 1 minus 5 is negative 4, 2. And 3 minus 5 is negative 2. So you have 4, negative 2. AB equal to 0, 0. And then you can see that the top row says negative 4a plus 2b is 0, right? Negative 4a plus 2b is 0. Good? And the bottom one is actually the same thing. It's 4a minus 2b equal to 0. It's the same as this one. It's not anything different. And actually, if you find the eigenvalue correctly, you will always find that the equation that you obtain from the top row is same as the equation from the bottom row, because in that analogy between two lines, when do you have infinitely many solutions? When the two lines are same exact thing. Okay? So you really need this line equation. If this was x and y, it would be a line in the plane, right? You want this line to be same as the second line. So that's always the case, okay? So you always get that. And then another thing is, because you have two unknowns, a and b, yes?
When you multiply for the second row, is it 4a minus 2b, or?
Yeah, 4a minus 2b equal to 0, which is same as this one, because if you multiply by negative 1,
Okay.
it's the same equation, right?
Why do you multiply by negative 1?
No, I'm saying that if you do this, you get this, right? If you multiply this, what do you get? 4a minus 2b equal to 0. I'm claiming that these two are same equations. Aren't they? They're exactly the same. If this was a line equation, say negative 4x plus 2y equal to 0, and solve for y, you get y equals to 2x, right?
Yeah.
If you solve this for y, you get y equals to 2x. So they represent the same line in the plane. Is that right? Yeah. So, and you need that in order to have a non-zero solution. That's what I'm trying to say. Okay? All right. And the reason you need it is because if you have two unknowns with just a single equation, see, this is redundant. This is the same as that one. So it's like you have two unknowns with one relationship between them. How many solutions do you have? You have infinitely many, right? And because you have infinitely many solutions, another thing that you realize is that when you have an eigenvector, it's not unique. So for a given eigenvalue, you may have infinitely many eigenvectors, because the eigenvectors are a comma b that satisfies this. And it's your choice to find the simplest one, okay? You can just find the simplest one that does make it work. And one easy choice is to just reduce to the lowest terms as much as possible. If you have negative 2a plus b equal to 0. And then what you do is you switch this, you put the coefficient of this into b, and coefficient of 1 b into a, and then switch the sign of one of them. So I'm going to take 1 for a and b to p2, and it satisfies, right? So it's like this. If you have negative 2 and 1, you just switch. See, the coefficients are negative 2 and 1, right? You switch them around, so you have 1 and negative 2, and you switch the sign of one of them. I choose to switch this sign. And 1, 2, you can verify that it's a solution to this, right? So now we have a nice pair. We have lambda equal to 5, giving you the eigenvector negative 2 and 1. Okay. And that's, no, positive 1 and 2, sorry. Positive 1 and 2, okay? And this is not the unique one. You could have chosen negative 2, negative 4, or 2, 4. There are many different ones that's possible. Okay? Now let's try to find one for lambda equals to negative 1, case 2. Lambda equal to negative 1. You plug it back in here. You get 2, 2, 4, 4. Again, if you do a cross down, you do 2a plus 2b equal to 0, and this will be the same as the one down here. So you have a plus b equal to 0. And in that case, I guess if I say a is 1 and b is negative 1, that's the solution, right? So for this one, I get 1 and negative 1. So that's how you get an eigenvalue and an eigenvector. So the easiest case is when you have two real eigenvalues, and you can find one eigenvectors for each of them. In that case, this can be solved easily. Can we stop the video?